So we proved an important theorem, namely that if 1 is less than p less than infinity and omega is an open set in Rn with the Lebesgue measure, then continuous functions with compact support in omega are dense in LP of omega. And as a consequence, we proved that LP of omega is separable if p is less than infinity, and it is not separable if p is equal to infinity. Now, in the last thing when I mentioned the countable dense set is Pm and tilde union over M and N, not just PMN as I wrongly wrote. I have corrected it in the lecture materials. Okay. So now we will see some more applications of this particular result. So now we are going to prove a fairly important theorem. So this is called Lusin's theorem. Okay, so E contained in Rn, a measurable set of finite measure. F e to r, measurable function. Epsilon greater than 0, then there exists phi continuous support, compact support in Rn such that Mn of the set of all x in E such that phi x is not equal to fx is less than epsilon, and if f is bounded, norm phi infinity is less than equal to norm f infinity. Okay, so proof. So given any measurable function on a set of finite measure, it is almost like a continuous function, because you can find a continuous function which is equal to it, except possibly on a set of measure less than epsilon, and epsilon can be as small as you can choose it. Okay, so step 1. So n in n, positive integer, so we define En. So let En equal to set of all x in E such that mod fx is less than or equal to n. Then En is measurable and En increases to E. That is clear. Now E has finite measure. So Mn of En increases to Mn of E, implies there exists an M such that Mn of E minus Em can be made less than epsilon by 3. Define f tilde from Rn to R by f tilde x equals f of x if x belongs to Em, where M is chosen here, and 0 in E minus Em. Okay. Now f tilde is bounded because it's less than or equal to m, because otherwise it is 0. So it's bounded, and Em has finite measure. That's the set where f tilde is not 0. So this implies f tilde is integrable. That is, f tilde belongs to L1 of Rn. So then there exists phi n in Cc of Rn such that phi n converges to f in f tilde in L1 of Rn. and there exists a subsequence phi and k. Phi and k converges to f pointwise almost everywhere. All these things we know. Okay. Step 2. EM has finite measure and phi and k converges to f tilde pointwise, implies there exists a f contained in EM. Measure of EM minus f is as small as you like, epsilon by 3, and phi and k converges uniformly on f. Okay, so this is Egorov's theorem. We have said if you have pointwise convergence on a set of finite measure, then you can find a subset where the convergence is uniform, that is, it's almost uniformly convergent. Okay, so then by Egorov's theorem you can do it. Now f also has finite measure. Then there exists a k compact, k contained in f, measure of f minus k is less than epsilon by 3. So you have k contained in f, contained in EM, contained in E, okay, and therefore measure of E minus EM is less than epsilon by 3, EM minus f is less than epsilon by 3, f minus k is less than epsilon by 3, and therefore measure of E minus k is less than epsilon. So we have a compact set candidate now. Okay, so step 3. So k is contained in f, therefore phi and k converges to f tilde uniformly on k, implies f tilde restricted to k is continuous. But k is contained in EM, okay, and on EM f tilde is the same as f, and that is, so f tilde equals f on EM implies that f restricted to k is continuous. So you've got a continuous function which is equal to f on a compact set, and the measure E minus k is less than epsilon. So all we have to do now is to extend this function from k to all of Rn in a continuous fashion, keeping the bound in control. Okay, so that is that is a topological process which we know. So by Thier's extension theorem, there exists a G Rn to R continuous such that G equal to f on k and norm G infinity is less than or equal to norm f infinity on k, and that is less than or equal, that's equal to m. So norm G infinity is less than or equal to m. Okay. So step 5. So you use Thier's extension theorem. We can also use Urysohn's lemma now. There exists a phi in psi, if you like, Cc of Rn, 0 less than or equal to psi less than or equal to 1, and psi is identically 1 on k. Okay, so you have k, and then you take a slightly smaller open set. So the complement is a closed set. So you can find a psi between 0 and 1, which is 1 here and which is 0 outside, and that is the Urijan's lemma. When you have two disjoint closed sets, you can find a continuous function. Okay, then set phi equals g times psi. So this implies phi equal to g on k, and that is phi equals f on k. Okay, and norm phi infinity is therefore less than or equal to, since psi is less than or equal to 1, norm g infinity, which is less than or equal to m, which is less than or equal to norm f infinity if f is bounded. Okay, and you have all this, and therefore the mn of phi not equal to f, this is less than or equal to mn of e minus k, and that is less than epsilon. So this is the Lusin's theorem. Now normally in most books you would find Lusin's theorem proved using Egorow's theorem directly, and then it is used to prove that C infinity continuous functions with compact support are dense in LP. We have done the reverse case. We have directly proved that the continuous functions with compact support are dense in LP using step functions and so on, and then we have proved Lusin's theorem as a consequence of it. So both ways are possible. Okay, so now we will have one more application. Proposition. So 1 less than or equal to p less than infinity, f in LP of Rn. For h in Rn, it's a vector, define tau h of f. The translation of f by h is tau h f of x is equal to f of x minus h. Then limit h tending to 0, norm tau h f minus f in LP is in fact equal to 0. Okay. So proof. So by translation invariance, of Lebesgue measure, tau hf belongs to LP of Rn, and in fact norm tau hf p is the same as norm fp. Now let epsilon be greater than 0. Okay, so choose phi in Cc of Rn such that norm of f minus phi in LP is less than, say, epsilon by 3. Then this implies norm tau hf minus tau h phi is also equal to norm f minus phi in LP, just as we saw earlier, and that is less than epsilon by 3. So phi has compact support, implies phi is uniformly continuous. Now let support of phi be contained in minus a power n, some box, big box, you can put it there. Then there exists a delta greater than 0. We can choose 0 to be less than delta less than 1, because the smaller you go, the answer, the uniform continuity will be there, such that mod h, this is the Euclidean norm, less than delta, implies mod phi of x minus h minus phi of x is less than epsilon by 3 into, I am going to put 2 times a plus 1 power minus n by p for all x in Rn. This is the uniform continuity which we are using. Then mod h less than delta implies integral over Rn of mod tau h phi minus phi power p dmn is equal to integral. It's enough to do it where this function is not 0. Since delta is less than 1, the support of tau h phi will be in a plus 1 minus a plus 1. So minus a plus 1 to a plus 1 power n mod phi of x minus h minus phi of x power p dmn. And that, by our choice, this integral we have chosen it in a very special way, and therefore that is less than epsilon by 3 power p. Okay, so this implies and this implies that norm tau h phi minus phi in LP is less than epsilon by 3. And now the result is just triangle inequality. Norm of f minus phi in LP is less than equal to norm of f minus f minus tau hf in LP is less than norm f minus phi in LP plus norm phi minus tau h phi in LP plus norm tau h phi minus tau hf in LP, and that is less than epsilon, and that proves the theorem. Okay, so with this so the next we will take up the question of duality. We have a norm linear space, we have Banach spaces. We would like to know what is the dual of this Banach space LP of omega. So we will take that up next.